Haber-Bosch process is one of the most frequently used examples of the practical application of Le Chatelier's principle. By manipulating the pressure and temperature of this thermochemical reaction of gases, the yield of ammonia, the desired product, is increased. In this investigation, we shall study 4 different systems involving ions in solution. We will use Le Chatelier's principle to explain how the effect of changing one factor affects the system at equilibrium. Part 1 is the conversion of the indicator bromocresol green from its blue form to its yellow form. HBC is the simplified formula of bromocresol green. The materials we will use include a 0.06% bromocresol green solution, a 0.01 mole per liter of aqueous hydrogen chloride, a 0.01 mole per liter solution of sodium hydroxide, and 2 Erlenmeyer flasks. Into the Erlenmeyer flasks is 50 milliliters of distilled water and 20 drops of bromocresol green. Record the color of this solution in the data table. Into the first flask, drops of aqueous hydrogen chloride are added while simultaneously swirling the flask. The drops are counted until a definite color change is observed. Record the new color and the number of drops required for this change in the data table. Aqueous hydrogen chloride is continually added drop by drop until another color change is observed. Record the new color and the number of drops required for this change in the data table. Into this flask is now added the sodium hydroxide solution, 1 drop at a time until a definite color change occurs. Record the new color and the number of drops required to achieve it in the data table. Drops of sodium hydroxide solution are continually added to the flask until another color change occurs. Record the new color and the number of drops once again in the data table. You now have enough information to complete the analysis question for this equilibrium system. Part 2 involves the light yellow iron 3 ion and the colorless thiocyanate ion. They react together to form a complex ion that exhibits a red color. The materials we will use include 0.2 mole per liter solutions of iron 3 chloride, potassium thiocyanate, and potassium chloride, and a 1 mole per liter solution of sodium hydroxide. Into a beaker is 15 drops of iron 3 chloride and 15 drops of potassium thiocyanate. Note the color change as the reaction occurs. Distilled water is added to dilute the intensity of the color to make the subsequent color changes easier to see. Approximately 10 milliliters of this solution is poured into 5 test tubes. The test tubes are labeled A to E. Test tube A will serve as a color comparison to the other test tubes. Into test tube B we add 10 drops of potassium thiocyanate. In the data table, record the stress as the ion from the equilibrium equation that was added, the color change observed, and use the equilibrium equation to determine the direction of the equilibrium shift, to the left or to the right. Into test tube C, 10 drops of iron 3 chloride are added. Record the stress, your observation, and the direction of equilibrium shift in the data table. In test tube D, we add 10 drops of potassium chloride. Neither potassium ions nor chlorine ions appear in the equilibrium equation. Record your observation. Is there a shift in equilibrium? In test tube E, 10 drops of sodium hydroxide are added. Neither sodium ions nor hydroxide ions are in the equilibrium equation. Record your observation and direction of equilibrium shift. This will help you decide on what stress is present. Now you have enough information to complete the analysis question for Part 2 of this lab. Part 3 involves an equilibrium system using a cobalt-2 complex. The materials used in Part 3 include cobalt-2 chloride hexahydrate, a 6 mole per liter aqueous hydrogen chloride. We will also use a hot plate and a cold water bath. Approximately 0.3 grams of cobalt-2 chloride hexahydrate is added to 2 Erlenmeyer flasks. Into the first flask we add 10 milliliters of aqueous hydrogen chloride and swirl the flask until the solid dissolves. Into the second flask we add 10 milliliters of distilled water. Swirl the flask to dissolve the solid, then record the colors of the solutions in both flasks in the data table. Distilled water is gradually added to the first flask until a definite color change occurs. Record the stress applied to this system, what the new color is, and the direction of equilibrium shift in the data table. The first flask is now placed onto the hot plate and gently heated. When a definite color change occurs, record your observations in the data table, as well as the direction of the shift in equilibrium. Finally, place the first flask into a beaker containing the cold water. Record the change in color and direction of equilibrium shift in the data table. You now have enough information to complete the analysis questions for this equilibrium system. In Part 4, we will examine equilibrium involving copper-2 complexes. The materials we shall use are a 0.1 mole per liter solution of copper-2 sulfate, 6 moles per liter aqueous hydrogen chloride, and a 1 mole per liter solution of ammonium hydroxide. The copper-2 sulfate solution is added to the Erlenmeyer flask. Record the appearance of this solution in the data table. Next, add 3 drops of ammonium hydroxide to the Erlenmeyer flask and swirl the solution to mix the contents. Observe the result and record its appearance in the data table. The ammonium solution continues to be added to the flask and mixed until another change occurs. Record this change in the data table. Finally, the aqueous hydrogen chloride is added to the flask, drop by drop, and mixed until a change is observed. Record this change in the data table. You now have enough information to complete the analysis question for this equilibrium system.